Hi everyone, myself Dr. M. Lakshmi Prasad, working as a professor in the Department of Computer Science and Engineering in the Institute of Aeronautical Engineering. So, in this video, I'm going to discuss about representation of a graph. So, what is a graph actually? So, graph is nothing but a set of vertices and edges. So, which is going to be represented as G is equal to V of V. So, V should be the set of vertices and E should be the set of edges that are connecting to the vertices in V. And so here the edge is going to be represented as UV. So it should be nothing but the pair of vertices. So here the vertices should be written as ABCD, which should be the vertices in the graph. And the edges is nothing but the combination of starting and ending vertex. So this should be E1. So edge from A to B, and this should be E2. So A to C, and from A to D, B to E, C to D, C to E. So these are the set of edges in the graph. So the graph is nothing but a set of vertices and edges. So which is going to be represented as G equal to set of V comma E, where E should be set of vertices and the edges is nothing but the line segment between the two vertices. So applications of graphs. So mainly this graph is going to be used in many electrical circuits and then networks of roads, flights, and various communications. So for that one, the graph is going to be one of the best example. And in electronic nodes, circuits, we can able to consider their points between them should be as vertices, and these lines between them should be treated as edges. And then similarly, the cities are going to be represented with the nodes, city vertices, and the lines that is connecting between the two cities should be represented as edges here. So when it comes to terminology, if the V0, V1 is an edge in the undirected graph, so then V1, V0 and V1 are said to be adjacent, and this edge is incident on the vertices of V0 and V1. Similarly, if there is an edge in the directed graph, then V0 is adjacent to V1 and V1 is adjacent from V1. So that means if there is an edge from V0 to V1, then V0 is adjacent to V1 and V1 is adjacent from V1. So the degree of the vertex, so the degree of the vertex is the number of edges that are incident on the vertex. For the directed graph, so the indirect degree of the vertex V is nothing but the number of edges that V has the head, and out degree of the vertex V is the number of edges that vertex has a tail. Okay, so if I'm going to consider a graph, so in this one, the number of edges that are incident to the vertex V1 should be treated as in degree, and the number of edges that are leaving from the vertex should be treated as out degree here. So if di is the degree of the vertex in the graph with the n vertices and e edges, so the number of edges can be write it as the formula E is equal to sigma 0 to n minus 1 di by 2. Okay, so if degree of the vertex is I in the graph, then with the n and edges and vertices and e edges, so the number of edges is going to be equal to the equal to sigma of 0 to n minus 1 di by 2. So example is that, so directed graphs and indirected graph. So in case of undirected graph here, so the degrees of this vertex is, so 1, 2, 3. So that's why 3 here. Similarly, for this one, the number of what is the degree? So 1, 2, and then 3. So 3. For this one, so 1, 2, and 3, 3. So like this, the degrees are going to be calculated. So in this one, in this graph, so the degree of leaf, these last level nodes will be 1, and for this the degree is 3, and for this one the degree is 2. So whereas in case of directed graph, so we have two types of degrees. The sum of the degree of the vertex should be calculated as in degree plus out degree. So in degree means the number of edges that are incident to the vertex should be treated as in degree, and the number of edges that are leaving from the vertex should be treated as out degree. So in degree is 1 and out degree is 1 in this case. And for the vertex V1, in degree is 1 and out degree is 2. So for the one how is getting 2 out degree. So this is one leaving edge and this is another leaving edge. And in the case of this one, the in degree is 1 and there is no outgoing edge, so that's why it should be 0. Terminology means is nothing but the sequence of vertices such that the consecutive vertices vi and v plus 1 are said to be adjacent. So in this one, uh, suppose the 3 are adjacent to and 3 is adjacent to 3. So this is the edge. Suppose if I'm going to find the path, right? So what is the path here? So A to B, B to C, C to E, sorry, E to C, C to D, and then C to E. So this is one of the path. However, I can able to write it as B to E, C to D, and E to C. This is another path. So like this, we can able to mention the path here. So if the path is starting and ending is same, then what we call it as a cycle here. So this one should be treated as source, and E, if I'm going to consider E here, this should be called as destination. So in the path, if there exists an edge, whose source and destination is different. If there exists the same source and destination, then the graph will what we call it as cyclic graph. Then path is nothing but no repeated vertices should be treated as a simple path, and the cycle is nothing but the path which contains the cycle. So that should be the where the last vertex and so source vertex is same. So connected graph. So a graph is said to be connected if there exists an edge from every pair of vertices. So since there is no edge from this one to this one, so this one what we call it as a unconnected graph or disconnected graph. So if every edge is connected from one vertex to another vertex, that should be treated as a connected graph. Subgraph is nothing but subset of vertices and edges form a graph. And connected graph means maximum connected graph is treated as a connected component here. Suppose if I'm going to consider a 3 vertex, the maximum possible graphs. So I can also be calculated here. Subgraph of the graph. So I can able to write it as so many combinations will be up here. Suppose the number of vertices is 3. I can able to get 3 power 2 cube combinations of subgraphs here. And similarly, if n equal to 4, I can able to get 2 power 4 combinations of subgraphs. So in this graph, so these are the subgraph. This is one, and this is another subgraph, and this one is another subgraph, and this is another subgraph. So whereas in case of directed edges, it should be counted one. So whenever there is an edge, directed edge, that should be only the constraint. So this one graph, and this another graph, this another one, and this another one. So normally you are going to see a tree and then forest. A tree is nothing but a connected graph without cycles. And forest is nothing but a collection of trees as well. Okay, so every tree become a graph, but every graph will not become a tree. So this is the difference between the tree and then graph. And connectivity, so let n be the number of vertices and b should be the number of edges. So a complete graph is one in which all pair of vertices are said to be adjacent. So what is the equation that is going to be calculated for the total number of edges in the complete graph? So that should be write it as m equal to n into n minus 1. Suppose if the graph is not complete one, so the value should be less than m. Okay, so here m should be the number of edges. So suppose if n equal to 3, the number of edges in the graph should be 3 into 3 minus 1 by 2. So 3 into 2 by 2, that should be 3. So the number of edges, suppose the number of vertices is 3, so the number of edges is also 3. So I'm going to write 4. The number of edges will be 1, 2, 3, 4, 5, 6. So 4 into 4 minus 1, that should be 3 by 2, 6. So like this, we're going to be calculate the number of edges of the graph. Suppose if the graph is not incomplete, so whatever value is there, so this value should be less than that of this value. So let's see the example. Suppose we're going to have n vertices. That should be 5, 1, 2, 3, 4, and 5. So the total number of edges will be m into n minus 1. So I'm getting 4. So 1, 2, 3, 4. So in case of not connected one, number of edges is 5. The number of edges is equal to 2 minus 1 and 1 minus 0. So that should be 3. So what is the directed graph here? So whenever the edge is going to carry a direction, then it should be treated as a directed graph. So here the edge is having the direction, here also direction. So that's why what we call it as directed graph. So what is the difference between the directed graph and undirected graph? So undirected graph is one in which pair of vertices and edge is unordered, and directed graph is one where the edge is directed pair of vertices. So whenever the graph is going to hold directions, then it should be treated as directed graph. If I'm going to hold undirected edges, then it should be called as undirected graph. So graph representations. So there are two types of representations: adjacency matrix and adjacency list. So what is this adjacency matrix? So let G is equal to, we come up with a vertex, the graph with n vertices. The adjacency matrix is a two-dimensional array, so in which the edges is going to be represented 1. So whenever there exists an edge from one vertex to another vertex. If there is no such vertex in the graph exists, then I can able to represent it as 0 here. So the adjacency matrix for undirected graph is symmetric, whereas the adjacency matrix or diagram may not be symmetric. So these are the basic terms you have to learn. So G be the graph with n vertices, and adjacency matrix of the graph is a two-dimensional. And if there exists an edge in the graph, then it should be represented as 1. If there is no edge, then it should be represented as 0. So this is the adjacency matrix representation. So in this graph, so I'm writing 0, 1, 2, 3, 0, 1, 2, 3. So whenever I'm going to have an edge from 1, 0 to 1, so I'm going to represent it as 1. So next one is 0 to 2, and 0 to 3. So that's why I'm representing 1. Otherwise, I have to represent 0. So there is no edge from 1 to 3, 1 to 2. So that's why I'm going to represent it as 0, 1 to 1. And it should be 1 and it should be 1. So 1 to 1 there is no edge. So that's why I'm going to represent it as 0. So in case a directed graph, so 0, 1, 2, 0, 1, 2. So there is an edge from 0 to 1. So 1 remaining all are zeros. So 1 to 2 and 1 to 0 and 2 there is no edge. That's why all are zeros here. And similarly, I can able to represent the same thing in undirected graph also. So what are the metrics we have to be follow in adjacency matrix? For the adjacency matrix, we have to determine the connections of vertices. That should be easy. So the degree of the vertex should be write it as in the form of matrix 1. For the diagraph, the row sum is out degree while the column sum is in degree. So the instance of the vertex y should be the summation of values and out degree should be the summation of values, where the row sum is equal to the out degree and the column sum is equal to the in degree. So for the adjacent matrix, we have to determine the connections of vertices. That should be easy one, and the degree of the vertex should be presented as in the form of matrix. So how can able to write the code in adjacency list? So for that, we initially have to define the matrices of 50 size and type of struct node pointer, and within this we are going to represent vertex variable and then we have to represent a struct node and then link variable. So the node pointer graph vertices where n should be 0. So this should be the adjacency list representation of the graph. So here what are the vertices are there, we have to be take it out. Then what are the vertices that are connected with 0? I'm writing here that should be 1, 2 and then 3. And for 1, what are the edges that are vertices that are connected? So 0, 3 and then 2. So like this we are going to represent the adjacency list representation of the graph for the directed graph as well as undirected graph also. A graph which is going to have n vertices and edges, so there should be n nodes and head nodes and 2 e list nodes. So where a should be the edges here. So what are the common operations I'm going to perform on this one? So the degree of the vertex is the undirected graph, and the number of edges hash is going to represent the number of edges in the graph and should be determined by the estimate of n plus 3. And our degree of the graph should be the number of nodes in the adjacency list, and number of in degree of the vertex in directed graph is nothing but traversing the whole data structure. So what is the graph traversing here? So the traversing is nothing but visiting all the nodes in the graph. So there are two types of traversals, like depth first search and then breadth first search. So for this one, how can I able to describe here is that, so if I'm going to have a graph like this, so 1, 2, 3, 4, 5. So first visited vertex is 1, and next breadth wise, so what are the next level nodes? 2, 3, 4, and next level node is 4. So in case of DFS, so it should be 1. So after 1, it should be 2. Then after that, it should be 5. So once I go back the backtracking, 1, 2, 3, and 3 to 4. This should be the level by level. So 1, 2, 5, 3, and then 4. Depth first search, this should be the level by, for every level you have to visit only one node. Then I have to implement the backtracking here. So depth first search in undirected graph is nothing but a wandering in a labyrinth with a string and then can be red paint without getting lost. So when I'm going to start vertex S, so we have to tap the end of the string to the point and painting as visited. So we can also travel along the arbitrary edge, and if there is an edge, so to an already visited vertex V, then we have to return view. Otherwise, if the vertex is unvisited, then we have to be moved from V, where V should be the visited one. And breadth first search is the one, so we are able to traverse all the connected components, and in which we are going to traverse all the nodes in the one level, and again we have to go for the next level. So what are the nodes that are present in the second level, and what next one, what are the nodes that are present in the third level. So breadth is, that should be breadth first search. In depth first search, so have to visit all the nodes in level by level. So if this is completed, then we have to again go back to the backtracking, and then again we have to be search what are the next level of nodes. Once this one is completed, again I have to go for the next one. This should be the depth first search. So see here, if I am going to consider this as the starting one. So in this starting one, so the edges that are connected to A is, so vertices that are connected to BA is, so BFE. So once this one is completed, then again I have to check first for B. So what are the edges that are connected? C here. And next one for E, I. For F, I. So that one is not connected, already visited, and this one is also not visited. So for I, so these two are going to be connected. So like this, we are going to be represent all the nodes in the graph. So what are the applications mainly? So find the path from source as to destination, and using graph we can able to search the starting address and what should be terminated as soon. So normally I'm going to use depth first search and breadth first search. So what is this DFS process? How we're going to implement it? So normally this implementation of DFS, we need a data structure called stack here. So in this diagram, so I'm going to start here. So initially I have to push the starting node into the stack. So what are the nodes that are connected to A? That should be B only. So that's why I'm going to push B into the stack. And next one, uh, C I'm going to consider. So C is the next one pushing onto the stack. And what should be next one is D. So D is going to be pushing onto the stack. So like this, we're going to be call the DFS by using the stack data structure. When it comes to BFS, we have to make use of queue here, queue data structure. So in this queue data structure, so initially have to be have to be insert the first one into queue. So what is the next one? B. So next one C, and from D. So like this, I'm going to insert all these nodes into the queue data structure. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.